Hi, everybody. This morning we have a session entirely dedicated on radio perspective on the topic of AGN surveys. So Francesco de Gasperin will first give an overview, general overview on radio surveys, their content, their importance, and so. And then Beatriz Mingo later on, she will focus on AGN content and more on the AGN content. We can
I can start. Okay. So welcome everyone. I will start with this overview on radio surveys so that you know exactly what's going on in the radio world at the moment. So
working.
okay, so there is this saying that we are in the golden age of radio astronomy. We were in the golden age of radio astronomy definitely in the past 10 years because a lot of new facilities have been built for a number of reasons that I will discuss now. From 2010, we saw ALMA, the expanded VLA, so the upgrade of the VLA, LOFAR in 2012, MWA in Australia, Meerkat in South Africa, the upgrade of the GMRT in India, and ASCAP in Australia, so, and Apertif, that is an upgrade of Westerbork telescope in the Netherlands, and also like new networks of radio telescopes creating, for example, the Event Horizon telescope, that is very famous for the image of the supermassive black hole. So why this happened in these 10 years? So because radio astronomy has been almost always computationally limited, and now computation became much better. The computing power is increasing steadily, and with this we could upgrade the telescope in a way that we couldn't do in the past. So now we have a wideband. We can use the entire wideband. This is definitely true for some telescopes that are called software telescopes, like LOFAR MWA, that moved a lot of the hardware problems, for example, steering antennas, into the software regime. But this obviously means that you become quickly limited by your ability of computer to do stuff. The other thing is that we have SKA coming. And SKA came with a lot of excitement and a lot of money. This also helps. And so a number of telescopes that were the Pathfinder and precursor of SKA received a big boost. So LOFAR is a Pathfinder, NWA, Meerkat, and ASCAP are precursors, means that they are really in the same locations and they prepare the stage for SKA. And UGMRT and Apertif are also Pathfinder, so they explore the techniques and the technologies that we use for SKA. So why we need all these telescopes, these different frequencies, different baselines, and so on? Because science is wide, and we need to address many problems in radio from the perspective of the band that we are observing it, but also the resolution that we need. For example, very high resolution here, 230 megahertz with the Event Horizon telescope, we can see the black hole at the center of M87. If you go a bit lower in frequencies with VLBA, which is another VLBI, so very long baseline interferometry array in North America, you can, at 43 megahertz, you see the part of the jet. Then you go lower frequency with the VLA, 1.5 gigahertz, you see the extended emission, the FR1 part of M87. If you go to even lower frequency using LOFAR at megahertz, hundreds of megahertz regime, you see the long-term integrated effect of the supermassive black hole on the environment. So I divided the talk in two parts. I will start discussing modern radio surveys, and then I will focus a bit more on LOFAR because this is what we do, and because in the Northern Hemisphere it is becoming a bit the most relevant facility for radio AGN stuff. So these are radio surveys from a recent review. This is the year, the date of first publication. The number of sources, you see there is a trend, an increasing trend. There you see the first famous surveys like 3C, 4C, Bologna survey here. And then suddenly there was a first wave of large surveys that covered like a wide area and then arrived to millions of sources. And you can recognize the famous surveys like MBSS and FIRST with the VLA and WENS with Westerbork and so on. So the first wave arrived when interferometer technology was ready. This at that time was still narrow band and was in the 90s. And also they had enough computing power, and they can devote enough telescope time to observe very, very wide array areas. And then there was a second wave that arrived more or less in these years, where we had a factor of like at least 10 in the number of sources that we could measure. And this is driven by technological improvements. We had feed and phased arrays that we didn't have at the time that improved the survey speed a lot. We have wideband receivers, so we can go much deeper in much less time. Again, survey speed increased. And we have more computing power and better algorithms, so we can do much more now. And so we are now at the tens of millions of sources covered by, for example, Mingo with ASCAP or LOFAR skies, or the surveys of LOFAR. So these are some surveys of the past that are still interesting to use. So I wrote here some relevant aspects. So if you are interested in some parts, then you now have this as a reference, you know which survey you can look at. So in the past, we have WENS that was relevant because it was a low frequency survey. At the time was the one low frequency survey. It covered only a fraction of the northern sky, but it was very good for the extended sources, although sometimes we had problem with the flux case of that survey, so it must be used a bit with care. SAMS was relevant because it was the only survey available, large survey available in the southern sky. NVSS, probably everyone knows it, was very important because it covered 82% of the sky, so very, very large fraction of the sky. It was very reliable. I believe every time I saw a 2 sigma pixel in NVSS and I trusted it, then at the end it turned out to be something real. So it's very reliable, very good for extended sources, and is a large coverage, and also is one of the few surveys at the time that had polarization data. And then we have FIRST. FIRST is a bit smaller in size, in coverage, but has a higher resolution compared to NVSS. It was very good to detect the position of radio sources, although the extended emission was many times resolved out, so you cannot trust too much the extended part. For that, you have to go back to NVSS. These are more modern surveys that are either completed or almost completed. We have LOFAR. You see that now we have ranges. Here we have only one number because at that time was narrow band, and now we go on the wideband era. And LOTS is at low frequency, under 50 megahertz. It's very sensitive. Here you can see an image of it close to the coma cluster. It has a very good sensitivity to extended emission and very high resolution, 5 arc-second resolution, so relatively good. Cover only the northern sky. We cannot go too much low declination with low. Then there was TGSS, came out a bit before. It has an extremely high coverage of the sky, so almost the entire sky. It was done with GMRT in India, and it's low frequency and very good coverage. But you can see that the quality is a bit low. Then there is GLEAM. GLEAM is done with MWA in Australia. So it's very good for the southern hemisphere. It's low frequency and has a very large frequency range, and also provides spectral index information. So this is also like pretty unique. So this survey is really good. And these are some ongoing surveys. We have the LOFAR LBA Sky Survey. This is the one I'm working on at the moment. The peculiarity of this survey is that it's the ultra low frequency surveys at 50 megahertz. So we are really pushing at the lowest possible frequencies. We cover part of the northern sky. And then there is VLAS in S-band, so 2.4 gigahertz. Also cover a very large fraction of the northern sky, and it's very good for counterpart, even better than first year. You see the ability to recognize where is the HN core. And there is EMO. EMO is also done with ASCAP from the southern hemisphere. Is at the gigahertz frequency and will be the de facto standard until SKA, although the release is still coming, so there is not much data available at the moment, but they are putting out very, very quick. This is the current coverage. Also, they have polarization, so it's very interesting also for that part. Now I want to show you something with using MeerKAT. So MeerKAT is one of the best telescope at the moment, radio interferometer at the moment, and is a precursor of SKA, and is in South Africa. It will be incorporated into SKA. And I want to show you what we did on the Virgo cluster with Meerkat. Virgo cluster is a very good laboratory because it is a very close cluster, only like 60 megaparsec away. We have closest groups like Fornax and things, but these are Virgo is a bit more massive, so he has cluster stuff going on. It's dynamically young, so we have a number of subcluster falling in and a lot of activities. But there is a problem in the Virgo cluster from the radio perspective, that we have M87 at the center. M87 is a 1250 Jansky source, 150 megahertz, and this is a lot. At the level that we need a dynamic range of about 10 million if we want to reach the thermal noise in the surrounding region of M87. And 10 million dynamic range in radio is extremely high. I mean, nobody ever done it. The record is about 1 million or so in dynamic range. So not surprisingly, the surveys, past surveys in these regions, they have usually extremely bad data because obviously they were processed in the same way of all the other fields, but this region needs a super precise and different type of processing. So you see MVSS, TGSS, and RACs from the Southern Hemisphere also, they have pretty low quality at that part. But with the LOFAR, we could actually do much better. So if some images are not super clear here, I already posted on the Slack the PDF, so you can have a look in real time of what I show you. So the quality here is already much better compared to the past, and this is because we have now a precise pipeline to deal with M87. And this is the project that we are doing on the Virgo cluster. This is called the Victoria project. It's the Virgo cluster multi-telescope observation of radio of interacting galaxies in AGN. So we decided the acronym and then the science came on top. And here you see the quality in frequency and noise of all the other surveys compared to what we can achieve with this specific survey on Virgo, done with LOFAR LBA at 50 megahertz, LOFAR HBA 150 megahertz, and Meerkat at 1.4 gigahertz. And there are already a number of papers published with this data, mostly on galaxy evolution, but also on AGN. And this is the quality of Meerkat. Again, you can see much better on the PDF if you want. We have 300 pointings, so it was a bit of a challenge to schedule all these observations. But here you see the quality that we can achieve, like very nearby to the very bright source of M87. All these are like interacting galaxies. We see a lot of these tails of galaxy falling into the clusters. And we also did a good discovery. This was work by Angelina Spasic in Hamburg. It was one of my students at that time. And here we have an XMM beta model subtracted image around M49. You see that there is a tail of X-ray emission, mostly due to the infalling of this subcluster into the main cluster of Virgo. And there was this known radio emission from the AGN. If you go to the LOFAR image, you immediately see that this becomes much larger. LOFAR is much more sensitive, low frequency, sensitive, and also sensitive at larger scale, and also lower frequencies. So we could see all this steep spectrum emission around M49. And one lobe is nicely filling one cavity that was known, but was a ghost cavity at that time. And the other part is instead like following the trail of the X-ray. So it's a complex object. But here you can derive the usual power cavity and radio power relation and put it on the Beatriz plot. And here is where M49 stands at the very low part. It's nearby. We could go pretty low in power. Also M87, this was quite some work that we did. These are images of M87 at 50 megahertz, 150 megahertz, and 1.5 gigahertz. With LOFAR HBA, we reach very high resolution here because we also use some of the international stations, not all of them. It was a very careful decision there. There are some artifacts left here, but everything else is what you see is reliable. We also tried to push the resolution with LOFAR as much as we could using the entire European LOFAR array. And here you see at 50 megahertz a 1 arc-second resolution image. That is something that is not so common to see. The quality is not super final, I would say. There is still some work to do, but we are getting there. And in LOFAR HBA, we are at the sub-arc-second resolution, the same level that you could achieve before only at tens of gigahertz. But now we can see the jet at the like the low frequency part, so at tens of megahertz. And also there is a lot of details in the LOFAR images. We see a lot of these filaments. This is an old cavity filled with old plasma, and here you see other filaments surrounding the radio galaxy. We could put together LOFAR HBA and Meerkat data to do a spectral analysis. And here color-coded is the spectral index. Red is flat, and green and blue becomes steeper and steeper. And here you see that the surrounding of the famous here, that is this raising bubble of plasma, is a flat spectrum, probably underlying the fact that there the magnetic field has a higher value compared to the surrounding. So the magnetic field can be compressed or can be stretched in the regions surrounding the raising bubble. Also, we noticed that something that we couldn't see before, there is this line of emission connecting the two ears. Now this became quite similar to this one, apart from this disrupted part. And there is this line of emission connecting these two ears, which is probably another case of a collimated synchronous thread that was very recently claimed for the first time, connecting otherwise disconnected distant lobes of radio galaxies. These are probably pipes connected to the presence of pipes of magnetic fields, but the origin is still known. Okay, let's move now to the LOFAR and LOFAR surveys. 10 minutes. Okay, perfect. So let's introduce LOFAR super quickly for people that don't know some of the numbers related with this telescope. LOFAR observes at the very low end of the radio window. So we are talking about 10 megahertz up to 200 megahertz. Below the 10 megahertz, there is the ionospheric cutoff. So radio waves are bounced back, so you cannot observe from the ground anymore. We have many stations here in the Netherlands. That's what we call the Dutch array. And then we have other 14 stations, I think, spread around Europe, with 2 more stations, one in Bologna and one in Bulgaria, that will be built this year. So we are still expanding the array. And when you use the entire station, the entire array, you go in LOFAR VLBI mode, LOFAR very long baseline mode, which is a bit of a different type of data analysis, much more complicated, much more computing intensive. I'll show you later what I mean. There are 2 antenna types. One is the high frequency part, is the high band antenna, LOFAR HBA, high band antenna. We're working in the 150 megahertz range. Resolution Dutch array is 5 arc-second. Resolution VLBI is 0.3 arc-second. Typical sensitivity 100 microjansky beam. And these are like these patches of like these are covered with plastics antennas in the stations, and you see the antennas are just below the cover here. And there are like several antennas. It's 4x4 antennas every single block, and there are several blocks in every station. And then we have LOFAR LBA, is the low band antenna working really at the ultra low frequency part. It's 1090 megahertz. Resolution is 3 times lower because the frequency is 3 times lower. Sensitivity typical is 1 millijansky beam. And these are very simple dipoles that you can see here in the stations. So wires put on the ground and then connected with a coaxial cable to the local computer. We have 3 surveys at the moment ongoing in LOFAR. Here you see the frequency. So low frequency is this part here, and sensitivity. These are many of the surveys I mentioned before. So we say that this region here has been widely explored. So we are pushing a bit in the unexplored part. LOTS is the LOFAR 2-meter sky survey. It's the HPA survey that sits here. And this is the LOFAR LBA sky survey at 50 megahertz. And there is also now an attempt to do a survey in the decameter wavelengths, so between 14 and 30 megahertz. It's the LOFAR decameter sky survey. It's extremely challenging. We have a couple of fields done at the moment. We don't know how much we can will be able to do, but at least it's doable, depending from how benign is the ionosphere when you observe. And these are some images of Hubble 2256. It's a galaxy cluster with many also AGN activity. Here you see a very long radio galaxy here, in the three different surveys. So LOTS, LODS, and LODES. See, the lower the frequency you go, the more complicated everything becomes in terms of data reduction, but also the plasma becomes much more diffuse, and you see less structures. So everything is also more complicated by nature there. Also from these surveys, you can extract dynamic spectra, for example, to study planet-star interactions. Has been done. You can also do polarization analysis, and we have a whole work to do automatic cross-matching with optical data and redshift modeling. We will discuss in the next talk. This is the current status for the LOFAR 2-meter sky survey, the 150 megahertz HBA survey. This is the processing status, like a few days ago, and is more or less what will be released in the LOFAR, in the LOTS data release 3 that will happen at the end of this year. Here you see where MET7 sits, and you immediately spot the regions that are difficult in the sky. Another couple of spots are where Cygnus A and Cassiopeia A are located. And we go down to the declination 0. So now DR2 is public, which is about a third of this coverage, mostly the extragalactic sky. And the work was a lot. Was for the DR2 was 7 petabytes of data, 9 million CPU hours for the processing, and for a catalog of for more than 4 million sources. But the DR3 will multiply everything by a factor of 3. There are a lot of AGN studies that one can do in these surveys. These are, for example, just a compilation of only restarted AGNs. So if you look at each of these radio galaxies, you can see that each of them has multiple episodes of activities there, and there were like a bunch of them known before LOFAR. Every new discovery was a paper, but now we have like hundreds suddenly of restarted AGN, which are like relevant to understand the duty cycles of radio galaxies. We also have a lot of X-shaped radio galaxies and slowly reorienting radio galaxies, which also were very rare before LOTS, but now we have hundreds of them. We could also study giant radio galaxies. Very recently, there was this Nature cover of the largest radio galaxy ever discovered. There was a 7 megaparsec long radio galaxies. There were only like few hundreds with at least a megaparsec size known, but now we have more than 10,000 detected in LOTS with like a few record breakers. These are the implications for how long a radio survey can live, how stable can be a jet for such a long time. This is a radio galaxy obviously located in a low density environment, and it has implication on how radio galaxies can pollute with magnetic fields and particles, the whole large scale structure. An important things that we are also doing with LOFAR. Everything I discussed so far is LOFAR 2-meter sky survey. So you're just using the Dutch array with a few hour integration time per field. So that's basic thing that you can do, and it's already like, I believe, revolutionary from the radio perspective. But then you can push in two different directions, and these are these two directions. The first is that we can incorporate the entire European array in our data reduction. We have data for each field of all the international stations. We just couldn't process it. And I'll show you later why. But this means that every 5-6 second resolution image that we have published can go up to a 0.3 arc second resolution image. And this is the same object. You can immediately see how much you can gain there. Also, we have a number of fields that we decided to observe for up to several hundreds of hours, going extremely deep and reaching the sensitivity of 10 microjansky beam, which is extremely. So this is the image of the same field from the survey, and once you reprocess the entire hundreds of data set of the deep field. So regarding the VLBI path, so the deep going higher resolution. This is where we collected the data with international stations on the lots coverage. The international stations arrived slowly, one after the other. So at the beginning, we had not many stations. This is the initial data release one. You see this is pretty black because we didn't have many international stations at that time. But then more international stations were built. So we were, in the meanwhile, we were observing other fields. So then we could cover most of the northern sky with a large number of international stations, enough to indeed calibrate them. There are plans with the LOFAR2 that I will discuss later to reobserve this region so that we can have international stations, like a large number of international stations everywhere. And this is frequency versus resolution. And this is where we go compared to also other surveys. We really are pushing into a region that was not explored in the past. The main showstopper here is the computing time. There are at the moment two pipelines that one can apply to LOFAR lots data. One is going in a targeted mode. So you decide that you are interested in 10, 20 targets in your field, and you just isolate that targets, reprocess only that small patch of data at extremely high resolution. And that's doable, doable. To the process this for all sources that are more than 10 millijansky in the survey will take 71 years on a 164 CPU node, but you can decide a number of targets, and then you can do it on your own machine. Then the holy grail that we are trying to achieve is the LOFAR VLBI of the wide area survey. So having the entire northern sky at 0.3 arcsecond resolution. We have at the moment, I think, 2 fields done with ages of work. Like one was a PhD of one guy. And this will take, at the moment, 133 million CPU hours. So this is more than 200 years on one machine. But we had a factor of 2 to 3 improvement compared to 2 years ago. So we are getting much better with algorithms, and that's the direction to go.
Close to the direction.
Okay, I'll very quickly discuss the deep fields. These are the 4 deep fields that we are analyzing at the moment. So if you see your favorite deep fields there, you can contact me because data are available. Polarization, if you're interested, I will discuss. And there is the LOFAR LBA Sky Survey, last thing that I want to discuss. This is the first release, and green will be the second release, which is also improved compared to the past. Let me see. Yeah, okay, I go just to the conclusion. I have skipped over a bit the LOFAR 2.0 upgrade, which is what the telescope is undergoing at the moment, which will mostly boost the ultra low frequency part. So if you're interested in very low frequency observations and what will happen with LOFAR 2, please contact me.
Thanks a lot, Francesco. Okay, there is time for a couple of questions. So, Celine, and then.
Yeah, thank you very much. So I'm very troubled by these huge 7 megaparsec jets that you were showing. This is even, well beyond the CGM scale. So, we've been talking about the multi-scale effects of these processes. So question one is what you're thinking, in terms of, energy budget. And second, are we going to have this?
We have many objects that are on the megaparsec scale. These objects was like the record holder, but I don't believe it's something that is totally incredible. We have more than 10,000 that are more than 1 megaparsec in size. So these giant radio galaxies are not anymore like a special thing. They are difficult to identify because you see the image here. And you really have to, like, automatic software will have very hard time in thinking that this is a lobe, and this was the core. So that's a bit the difficult part. It's still a bit of a human inspection part. But I think this will become something that we can analyze with. In terms of the energy budget, I don't know. It's very hard to derive the energy budget just based on the radio part, because we obviously don't have any other wavelengths that here we can use, because we are in a very low density environment, so no X-ray, nothing else. So we don't have cavities, we don't have anything. So, but that's a good point.
You chose some very cool radio images of agents that were reactivating, that the jets were realigning. Maybe this is a very basic question, but how can you tell that from the radio data?
That are restarting.
Yeah.
Yeah, you see that these are typically FR2 galaxies where you have the two lobes here, and then you internally see two other small enhanced part of emission. So that's a really like a second burst of emission that is following the first one, and you see that is everywhere. So these are the old lobes, and these are the new lobes starting again from the center.
One very quick one.
Yes, it's very quick. So, but can you say maybe something on the average distribution of the spin of AGN, looking at the fraction, for example, of restarted in the same direction and restarting with a rotation?
Yeah, probably yes. I have not done the work. I don't know.
Yeah, not so much on spin, but there's plenty of work being done on precessing jets, which you do see quite often. So where the orientation angle of the jet changes, and obviously if you have some time off, you know, that looks like it's completely reoriented, but it's just moving gradually. There's lots of work done, not just, you know, within law for the past few decades on binary black holes, and, you know, when you can have one active and the other one, maybe you can get both on a radio place occasionally. Sometimes, you know, one is radiatively efficient, the other one is radiatively inefficient. It's very hard to find these things. So that one is quiescent, you can see it. So yeah, I think on spin specifically, I'm not sure whether anyone on the collaboration is working on this, because I don't know, I would not want to touch spin. There's a whole debate going on how you measure this and how realistically, you know, you can constrain this.
I think that for the sake of time keeping, we should move to the talks. Thanks, Francesco, again, and for the discussion. So, Beatriz, you can start sharing.
Is always down.
Exactly. If you still see the action. Yeah,
It's always rotating like this.
Yeah,
So the
on
it
the
is from here
transaction.
and it's always along the same direction. We're using some precision like
exactly
this.
on the precision. Yeah, yeah.
Oh yeah, yeah.
From the Gen Science from Radio Science.
I have to say, this is one of the hardest talks I've had to put together. And I think this is a very good thing, is because there's so much I wanted to cover. So this is by no means going to be comprehensive. It's going to be quite heavily LOFAR biased. But I thought I'd rather tell you about something that you can find interesting rather than try to cover everything and not tell you enough about the good stuff. So the first thing I wanted to highlight, you know, if you haven't worked with radio survey for a while, if you found these too terrifying, you know, that's okay. We do as well. You know, I've been doing this for a while, and I'm still terrified about you know, radio data reduction. But things have really changed in terms of usability. So in the past, you would get, you know, surveys like FIRST and MVSS, they would just give you components. They would not give you host associations. They would not even associate the components within, you know, with each other. And the documentation was very bare bones. So you were just kind of left on your own to figure out what you were looking at and whether that was useful for your science. That's definitely not the case anymore. So this is an example from the second data release of LOTS. You can go onto the LOFAR Surveys website, which you can see here. And you know, you click on the LOTS data release 2, and you have there's a catalog description up here that tells you a bit about everything, and then you have all of these resources, you know, virtual observatory resources, previewers, radio catalogs, radio optical cross-match catalogs. So we already give you the hosts so you can do your science, and the components are already associated, so you know that they belong to the same source. Spectroscopic classifications for some of the sources, various things, position search, cutout surveys, big mosaics, so you can do large area surveys and look at the images in beautiful detail. It's all science ready for you. And even then, if you stumble upon something you don't understand, you want to work with the radio catalogs themselves and throw them onto NWAY, for example, and do your own cross-matching, please do that. If you find that you get different results, tell us about them. This is always an ongoing process, and we always try to make these better. The cross-matching, for example, in case you're interested in this, we use a combination of methods. So we use a maximum likelihood ratio, which works quite well. So we have a very good idea of what galaxies tend to be the hosts of radio galaxies. And obviously there are exceptions, but they are still exceptions. So we get a very good idea even from extended sources on what's going to be the most likely host. We combine these with automated image analysis, and in particular, this method by Bonnie Barkus, which you can see here, where we use image erosion for some of these extended sources. And effectively, in steps, we can trace the path of the jet, and that gives us a line along which we can use the maximum likelihood ratio to identify the most likely host, to constrain the number of sources we need to do a search on. Obviously, if you're trying to match this on a circle, it becomes a much harder problem than if you know that your host obviously has to lie somewhere along this line, because the jet is coming from a galaxy. And then for some of the more complicated, more extended things, there's a visual inspection process, which initially involves the universe. So we put all of these up, radio and optical images for people to inspect. This is run by volunteers, but then for the very complicated cases, we also have experts having a second look. Because you do get, as you go deep, you start discovering lots of new stuff, and things can get pretty complicated, especially considering that these things exist in clusters and groups, and these are very messy environments. So these are some of the nightmares where you can see, you have these contours representing the radio emission, and you have all of these sources. Where the hell is this coming from? Or like this, you have contributions from more than one galaxy. How do you split this? Things that in the radio just looks like your perfect double lobed source, and then you look in the optical and no, it's merging galaxies, or these things here. But I really want to emphasize, this is all from LOTS DR2, by the way. I really want to emphasize that the vast majority of radio sources have sizes that are within 15 arc seconds in LOTS, which has a 6 arc second resolution. And at that point, all of these can be automated. The algorithm is clever enough that even if you have separate components for a source within sizes similar to this, the algorithm can associate them based on flux ratios, geometry, distribution, and so on, and how close they are to each other. So we still need to do visual inspection, and obviously, even a 6% fraction, when you have millions of sources, it's a very large number. But this is becoming easier and easier because we also, now that we have these massive samples, we can use machine learning algorithms and other numerical methods to train. So yeah, it's complicated, but it's not as complicated as it used to be, which is good. So yeah, Francesco already showed this plot. I wanted to emphasize, that things have also changed in terms of the numbers of sources. This is a logarithmic scale. So yeah, we're in the millions to tens of millions of sources here with new generation surveys. So we have 10 to 100 times more sources than we did in the reference surveys that everybody uses that were already revolutionary, 20, 30 years ago. So if you think about the radio sky and you think this is a very sparse thing where you can go for miles without encountering a radio source, think again. It's very likely that you can find the counterpart to what you're studying in the radio. And the SKA, which will come up in the next decade or so, will give us a factor of 10 more. So we also need to be prepared for this, and it's one of the reasons why the computational challenges of the SKA are huge. So the figure of merit here, so LOFAR, this is for the main area survey. For the deep survey, the SKA low and LOFAR will actually be pretty close in sensitivity. And in fact, LOFAR will have better resolution, but obviously one is in the northern hemisphere, the other one is in the southern hemisphere. But the truly revolutionary science will come from the higher frequencies. The SKA mid, SKA2 at these higher frequencies, that is going to open up, a completely new universe of optical. And now I have a question for you. I want you to tell me which of these two galaxies hosts an AGN. So we have this one here with these pretty high excitation lines, this one here without high excitation lines. So hands up for number one. Oh, excitation. Okay, hands up for number two. Good, I see some hands staying up because that's right, both of them are AGN. The one on the left is a very famous Seyfert galaxy in GC 5548. The one on the right is not a Seyfert galaxy, it's a boring elliptical galaxy. When you look in the optical, well, boring depends on who you ask, obviously. It's well in the eye of the beholder, but you know, when you look in the radio, you have this beautiful jet that in fact has a very complicated structure at small scale. So it's quite an interesting source, actually. So this is just a reminder that, you know, if you're only looking at things that look like this, and you think, you know, you base all your AGN population studies and on your source numbers and on your predictions on things that look like this, you're completely ignoring all of these things, which are very, very numerous indeed in the low redshift universe, to the point that they outnumber these things by a factor of between 7 and 10. So active black holes are active around. This is just an illustration to show you that we know as we go deeper in the radio, we also recover lots of star formation. So, you know, this is a comparison between HST lots and logs. So lots is the high frequency and logs is the low frequency survey from LOFAR for the Wormhole galaxy. And you can see just how beautifully we recover all of this free emission, in this case from star formation at both frequencies. So these radio surveys are also a very good way to put constraints on star formation rates and to help you separate the AGN from the star formation that's around it. So, this is some recommended reading. These are three recent reviews that give you a really good comprehensive overview of, you know, radio survey populations, the various properties of radio AGN. So if you want to learn a bit more about these things and what you're seeing when you actually do the cross match with the radio, which I hope you will do, these three are really good. The first two are a bit more general and focus a bit more on extended sources. This one by Chris O.D. focuses mostly on these compact populations. This is what the family picture of radio AGN looks like. We have compact, you know, this is luminosity versus size. So we have very compact sources up here, which are very luminous. We have the radio quiet populations down here, quasars and Seyfert. So we do see these ones, as you can see, obviously lower radioluminosities. They're a little larger in size compared to these things. Radio loud quasars are kind of up here. And then there's the FR1s and FR2s, so Farner-O'Reilly type 1 and type 2, that as radio astronomers love, and that's because they tell us something about the physics of the jet ISM interaction. But there's a lot more compact sources than there are extended sources, and this is already telling us something about the lifetimes of activity of these things. So not all of these compact sources grow into extended sources. A lot of these jet cycles are actually quite short and quite contained in time. And in terms of FR1s and FR2s, so you know what I'm talking about, the distinction has to do with morphology. FR1s are things that are bright in the center, FR2s are things that are bright in the edges. And this is telling us about where the jet is interacting with stuff and what it's disrupting. So in the case of center bright sources, the jet is disrupting early on. And this is a combination of jet power. So if the jet power is lower and the environment is denser, obviously this thing is going to disrupt pretty quickly. FR2s, they have faster jets typically, and they live in slightly slower, you know, slightly more sparse environments, so they disrupt later on, so they create these shocks at the end. So these things age from the inside out, the newer electrons are here. These things age from the outside in. So physics, yay. And this ties very nicely to, I'll try to explain, you know, what survey you want to use, depending on what type of science you want to do. It's always important to try and remember what science questions you're trying to answer. So this plot here shows flux versus frequency for a number of instruments. So LOFAR is here. These are your typical VLA and Meerkat survey. So this is where Mighty and Aegis Excel, that the surveys of Meerkat are going to be. And on my CR, I'm completely going to ignore ALMA because Stacey covered this a lot better than I ever could. I'm going to focus on these bands. And this is the synchrotron emission you would expect from your typical electron population that is injected through a jet. So if you have electrons traveling up the jet, they're going to emit synchrotron radiation with this power law shape. Now, these electrons, you know, you either switch the jet off, or these electrons actually come off the jet and then start, you know, spiraling into the lobes and just traveling around the environment. Because of the properties of synchrotron radiation, the more energetic electrons are going to radiate their energy faster than the low energy electrons. So you're going to start losing signal at higher frequencies, but you can still recover that signal at low frequencies. This is what we call spectral index, spectral aging. So if you ever hear these terms, this is the diagram you have to remember. And this ties nicely with the frequencies you want to use. So at high frequencies, because again, resolution, it goes in proportion to wavelength and inversely proportional to your size. So you need bigger telescopes. This is, high resolution is easier to achieve at higher frequencies. You are recovering more compact emission. This is really good if you want to map shorter activity timescales. So if you want to know what the radio is doing now, to compare to what your X-rays or your optical are doing now, for example, you want to focus on, these cores, compact cores, high frequency radio emission. At low frequency, the trade-off is you have much better sensitivity. You're much more sensitive to extended emission for these older electron populations. You can map much longer activity timescales. Ideally, you want to combine both. And we're getting to a point where you can combine both systematically with large surveys, but this isn't always possible. But always keep your science questions in mind. And I wanted to highlight, this is something that Francesco already mentioned, that with LOFAR, we're now going to almost home space telescope resolutions, thanks to these, very long international baselines. I like to call LOFAR the Dutch plan for world domination. And, you can go from 6 arc seconds to 0.3 arc seconds. And with these, obviously, you can constrain compact structures within your sources and do all these multi-frequency analysis and, do some physics on where the ISM fun times are happening. So if you want to understand what sort of populations you will recover with LOFAR, I think this paper here gives a very good overview. I've cited here, I put the slides on Slack so you don't have to worry about writing all of these down, kind of equivalent things for all the known surveys. So this is based on the LOFAR deep fields, and this is for 2 reasons. One of them is obviously we have more LOFAR sources there. These are deeper by a factor of 10 than the white survey, but also we have fantastic multi-wavelength coverage here, to the point that we recover 97% of the hosts. So we identify 97% of the hosts in these surveys. For the wide area survey, I think the match is about 75 to 80% or something, which is still incredible for, in radio terms. This is huge compared to past surveys. And the problem there is not that, that the radio is not good enough. It's we just ran out of optical data. We ran out of hosts. The optical surveys are not deep enough. So we have about 80,000 sources here on a smallish sky area, is 25 square degree. And you can see here, so that this is the fraction of sources versus the flux density, so how bright your sources are, and versus redshift. And this green line here combines radio loud AGN. This blue line here combines star-forming galaxies and radio quiet AGN. You have the split here. So radio quiet AGN are in red in these plots. This is the number of sources and fraction versus redshift, and again flux density, so how much flux you will recover. And this is something that has been observed in other surveys as well, because we recover many more sources with LOFAR. So at very low flux density, so very, very, very faint sources were dominated by star-forming galaxies and the star-forming emission coming from radio quiet AGN. Then we start getting bumps and some more emission from the small scale jets of radio quiet AGN, but we also start recovering more of the radio loud population. And the interesting thing here again is, if we split this radio loud population into lurgs and hergs, lurgs obviously vastly dominate. Particularly at low redshifts, less so at high redshifts. This is where things start catching up, where there's more gas available for everything, so you can go high accretion. And the black holes are also small. So for radio quiet AGN, we have 3 detection mechanisms to recover this in the radio. We can do that with star formation, we can do that with these low power jets, and we can also do this if there is anything driving a shock. There's enough of a shock in there that we can accelerate particles to where they can emit synchrotron radiation. So we're getting very good at finding these with radio surveys. But please, please, please beware, when you start doing these things, do not apply correlations and scaling relations blindly. I'm not saying, by no means don't apply them, because I do this. I did this plot in 2016 that has bolometric luminosity converted, calibrated from X-rays and from mid-infrared versus jet power derived from radio data. And this is the famous Rawlinson-Saunders correlation that says, there is a very narrow correlation between your bolometric luminosity and your jet power. And there is indeed a trend, as in obviously you put more stuff into the black hole, you can have more luminosity and you can have more jet, yay. But there's like 5 orders worth of magnitude of scatter in here. When you select these things in multiple ways, so if you only select SDSS quasars, which are these things, radio loud SDSS quasars, these blue things here, then you get a very narrow sampling, a very narrow slice of this. If you start putting more sources in here, like 2 Jansky and 3 CRR sources, which are some of the most powerful radio AGN in the universe, or the various populations of radio loud AGN, various populations of radio quiet AGN, the galaxies and the lurgs are here just to show you that you should not take them into account, but you can by accident put them into the plot, but they don't follow the same relation. But even just here, the scatter here is humongous, and there's multiple reasons for this. There's all these, these things are calibrated based on very bright sources. They don't work for everything. There's uncertainties in how we measure things. There's timescales involved. With radio, you're integrating over millions of years. With X-rays or millimeter, you're integrating much shorter timescales. So things change in that time span. So there's so many assumptions that go in here. Don't just assume that because you have an X-ray luminosity, you're going to have, that radio luminosity. Go and check, please, because otherwise you're making all the wrong assumptions. And also when you derive things, from cavity powers, and jet powers based on these cavities that we see, please do bear in mind that these are derived from specific sources. Most of them are FR1s, pretty quiet, pretty stable, effectively, and not wonky and or bent in any ways, and you can only do this for that population very carefully. So you can't extrapolate these results carefully for everything. It's one of the best things we have to try and extrapolate things. So it will give you an order of magnitude thing, but please don't take it as the end answer, the end all and the be all. And in terms of particularly these jet power or environmental density calculations based on radio or based on X-rays, these recent papers, like this Croston, give you some very good ideas of how you can make these predictions for specific populations. So for FR2s, bright FR2s, the ones that are edge brightened, these have much faster jets. They are electron dominated. They don't entrain as much of the environment as the FR1s, which are more proton dominated. And this gives you different correlations in terms of the X-ray luminosity versus the radio luminosity here. This is just predicted, measured. This is measured X-ray luminosity versus radio luminosity for a very well understood sample of FR2s. And this is the equivalent for a very well understood sample of FR1s. And it might be hard to tell just side by side, but these things follow completely different relations. And the shape of the FR1, whether it's bent or not bent, uniform or not uniform, has, that gives you slightly different relations as well. So do bear in mind that, you cannot do this universally. The physics involved are different. Obviously, if you have something that's traveling supersonically, you're driving a shock at the edges, shaking things about, that's going to give you a different pressure profile than you have something slow and steady that's just kind of buoyantly traveling into the intercluster medium. So just be careful. This is something I thought you would find interesting since we've been discussing this. The fact that the gas composition of a host does have a say into what the black hole does, but it's not a one-to-one relation. It's not as simple as that. So this is some work I published in. You can see here. So these are sources selected, only extended sources. So there's no small scale compact sources here. Most of your radio quiet sources are not going to be here. This is definitely very loud. So this is radioluminosity versus specific star formation rate. And I know there are caveats in terms of how you derive star formation rates. This is just to give you a proxy for the gas content of it. And the luminous, optically luminous X-ray luminous sources are surrounded by diamonds here. So those are the only ones you detect as AGN when you go into the optical or X-ray surveys. Everything else is a lurg, is a low excitation radio galaxy, is a radiatively inefficient. And in yellow, you have the FR1, which are the ones that I said disrupt early on, slow, steady jets. All the FR2s are in blue and in red. I divided them between high and low luminosity because of complicated things discussed in this 2019 paper. I will go into that. But there's differences in the two populations. And as you can see, most of the high accretion rate things are up here. But even up here, you're dominated by the low accretion rate things. So the 2/3 of the points up here are very high radioluminosities are still radiatively inefficient. And in terms of star formation rate, specific star formation rate, you can see that the HERGs, the high accretion things, are all in more gas-rich systems, which makes sense. You need the gas to be able to feed the black hole fast. And a lot of these, even at lower luminosities, are in hosts that are a bit smaller. But the fact that you have the gas, so in this histogram here, doesn't guarantee that you're going to have a high accretion rate AGN. So there's timescales to take into account. It's just, has this gas just not made its way into the center yet? Is it just traveling through the galaxy towards the black hole? or has it already gone to the black hole and there's been something that has quenched star formation in the middle and has kind of starved out the AGN in the middle, but there's still some star formation going on in the outskirts. You know, the time scales of this, tracing what, you know, how this accretion switch happens is something that we need to investigate. Oh gosh. So this was something that, again, Hannah covered yesterday. Is just a reminder that you can have jets in radiatively efficient sources. The radio loud, radio quiet thing is not a dichotomy, it's a spectrum, because it's based on a ratio. So if you have something that is dominated by the X-rays and you do an X-ray versus radio comparison, obviously this is going to come up as radio quiet. But if you have a low wimpy, low power wimpy jet in there, that's still going to come up as radio quiet, and it's still going to have a jet, and that jet can wreak havoc into the host galaxy or even larger scale environments still, even though it's very low power. So don't just discount and assume that you don't have a jet just because something is radio loud, radio quiet, because that is that's a ratio. It doesn't mean that your jet is not there, that emission is zero. And this is an example of a radio quiet AGN, so Sarcinus, which has a measurable jet. This is something that it's a source that's nearby, and it has everything going on. It has a circumnuclear star formation ring, it has a bar, it has an outflow, and it also has a jet and a lobe. So there's all sorts of stuff, and it's in this regime. While this is your typical, radiatively inefficient thing, X-ray cavity source that you typically think about as a radio source. And these radio quiet jets have become pretty ubiquitous in the literature recently. We're finding them everywhere. They're pretty common apparently in quasars, in radio quiet quasars, but there's a lot of debate going on. So I put some references here, but the reference, the paper I want you to look at, which compiled with this review by Chris Harrison and Cristina Ramos Almeida, which covers all of these. There's a lot of debate going on whether you can produce these radio emission simply through radiatively driven shocks that cause particle acceleration and cause some of the radio emission to happen. I think that this is a teacup quasar. It's one of the more famous examples. I think the answer for some sources, the geometry and the energetics say this is definitely a jet. In some other cases, it's more complicated, and sometimes it's very hard to separate. You do have an outflow, you do see the outflow, but that outflow might be driven by the jet, even though some of the emission that you're seeing is from the shock. The jet is still there, and it's doing stuff. I wanted to briefly mention galaxy scale jets. This is where you see the lobes interacting with the environment of the host galaxy, and we're finally, in the past, we've been able to do this in X-rays and radio for a few nearby sources where you can actually put, so get some X-ray data. This is Sarcinus. This is from my own PhD thesis. This is how long ago this was. And this is the radio where you see shocks going on. You even see some magnetic field compression and amplification of the radio emission here, which is cool, just math physics. And then you can do this with X-rays and trace the shock conditions of the lobe, do some very nice energy derivations on how much energy these things are putting into the environment. And there is a bit of a scale and relation. I do have that slide from 10 years ago, or 15 years ago, when I presented this, in case you're curious about this scaling. So this is good. We can do detailed physics, and we have a very good measure of how much energy this interaction is dumping into the host. And we'll find that you can dump 10 to the 4 to 10 to the 6 supernovae worth of energy over a few million years directly into the ISM of these galaxies. So that's AGN feedback in action. But we can only do this for a very, very small number of sources, and this is dwindling because our X-ray telescopes are losing sensitivity. But now we can do this statistically with global surveys, and these are two recent examples. So there's a few papers here. This is a paper by John Chilufya, looking at very small scale emissions. So this is 2.4 kiloparsecs. These are really wimpy sources that are also radiatively inefficient. So these are fairly small black hole masses hosting these very small scale sources. We don't know yet how long they're going to be, but this still has the potential to wreak havoc into the circumstellar environment, into the circumnuclear environment. While these sources from Webster et al. 2021 and AAP, they're a bit larger scale. These are kind of the same size as the host galaxy, and we see them at different activity timescales. Some of them are active. There's one that's fading, and there's one that has hints of restarting activity. So these are pretty ubiquitous. It's just very hard to study them. This also allows us to put some constraints on the ages of activity and the ages of recurrence of these sources. So for compact sources, which I said don't always grow into the bigger sources, some of them are so short-lived, you know, that they are under a mega year old, under a million years old, and they tend to recur. We do see them recurring on time scales of 10 to 100 million years. But obviously these varies widely from source to source. This is Mercurial 6. This is a good representative of galaxy-scale jets, along with the Milky Way, which has remnants of radio bubbles, the Fermi bubbles here, and these are the ones found by Meerkat more recently. For these sources, we can trace their ages back to about 50 million years or so, between 1 and 50 million years, and the timescales of recurrence are pretty similar. This is how often the jet switches on and off. While for bigger sources like the FR2s that Francesco showed, you know, a lot depends on what your hosts are and, you know, how you're accreting and what your supply of gas is. So the FR1s, the typical, you know, brightest cluster galaxy thing that's, you know, have slow, steady jets that use regular cavities, these tend to have elliptical hosts, and they are nearly always on. So these jets, you know, you need very, very little energy, actually, very, very little gas to just keep things fed for a very long time. The ones that we see restarting and recurring, like the ones that Francesco showed, like these ones here, they are typically in more rich hosts, and you can actually see them restarting on, you know, it doesn't mean that other things don't restart. These are the ones that restart on timescales that we can observe, where we can observe the newer phase and the older phase. And I'm going to be pushed away. So, yeah. These life cycles also allow us to map larger scale emission. Like, this is a beautiful paper by Marisa Brienza. There's two actually, where you can map some of this incredibly chaotic, beautiful emission that happens in clusters, which are very messy environments where everything is going on. And you can trace back the history of the emission in some of these sources, you know, between, you know, 100 and 220 million years, putting very good constraints on activity timescales and also the timescales of intermittent. I very quickly wanted to mention there's some really cool studies done recently with VLAS in terms of AGN variability, where, you know, we see process transitioning from radio quiet to radio loud on timescales of about 30 years since first was released. You know, these things were not there. Suddenly on VLAS, these things are incredibly radio bright. So do have a look at this. It's kind of breaking our paradigm of, you know, jets being kind of a slow, steady thing that happens forever. You can see accretion changes affecting radio emission on timescales of a few decades. So we definitely need more monitoring campaigns to look into this. I wanted to very, very briefly mention, this is almost the end, new ways to find AGN, you know, based on spectral index differences between different surveys. You can categorize some of these sources and find AGN activity in this way. This is the brightness temperature selection that somebody mentioned the other day, led by Lea Moravito, where we can physically separate in low far because of these very high resolution observations, the emission from the AGN in the center, you know, at 0.3 arc seconds, well, from Hubble regime, we can separate the AGN from the star formation emission in radio, which is incredible. And you can find all of these sources kind of in the transition between star formation and radio excess that we were completely unable to identify before, you know, either in radio or at, for your X-ray surveys and so on. A few things to think about. You know, that these are things that we have been discussing this week, you know, as well as black hole seeds, which I've put here. The winds versus jets discussion. You know, with LOFAR, we're now mapping very long time scales of activity. So we're mapping together the restarting sources, remnant sources, and active sources. Are we mixing pairs and atoms? And I think the answer to this relies on what kind of activity timescale you're interested in. If you're averaging over a long time, it doesn't matter if things flicker on and off, but obviously you can't relate that to what the X-rays are doing, because, you know, that's instantaneous, the other one is long term. How do we do this? How can we best address all of these baked assumptions that we have discussed this week? What physics can we inject into simulations? Are we prepared for the SKA? I think the answer is no. And yeah, just I'll leave it with this. Please join the radio site. There's all of these that you can do with the science.
There is time just for one question, because I really wanted to leave some time for the discussion, at least half an hour. So I think Shaki was first. Maybe we can go ahead with the discussion.
Thanks for the nice talk. I was curious about, you know, the effect of radiomorphology on the ability to kind of offset these cooling flows in the central movements, and how that then impacts the rates or the blurred nature. So I mean, like, if they push out the gas in these FR2 kind of cases, maybe they're not doing most of the damage in the central region. So
yeah, so this is an ongoing thing, and this is something I'm studying at the moment, something I'm really interested in. So down here, you have very low luminosity sources that still have an FR2 morphology, and they are in hosts that are relatively low mass and relatively high star formation rates, similar to our Milky Way. We haven't seen these before. We thought that these things were extremely rare. Maybe we found the odd one or two, but we thought that these things were pretty rare, and now we're seeing a whole population of them with low FAR. And we don't know how much they contribute to all of this. They're still FR2s, they're still pretty large, so all of the energy is being dumped at large scales rather than at small scales. And we don't know, they're low power, but they're still doing something. We don't know how much they contribute to large scale AGN feedback. So for all of these new populations that we see, these low luminosity populations, this is still very much a question. This is something I'm working to address with my fellowship. For the luminous ones, I think the answer is a bit more clear. These are the ones where we have been able to observe, X-ray environment from many of them. Not for all of them, by no means. These things live in groups rather than in clusters, and then getting the X-ray emission is a lot harder. But we also get better constraints from optical surveys and things like Euclid, eventually LSST. We, for example, they're gonna give us much better constraints on the numbers of galaxies, their redshifts, so we can actually associate them and see where we have a group or a cluster that is a bit harder to identify in X-rays, for example. And then we can start making better environmental predictions for these things and better constraints on how much energy these things are putting into there based on the environmental density. Perhaps. Does this answer your question?
Thank you. Thanks again, Beatriz. I think we can kick off the discussion. So if Francesco, Silvia, Giovanni, and Beatriz can bring their chairs up here. I will keep an eye out for sharing a bit this session. Otherwise, it's and I will intervene only if something is going too wildly or somebody's not noticed.
So believe that.
So we have tried to put together some we have tried to put together some questions discussion part, so based on what we have seen in this week, as we were discussing in the previous talk. We can you can read that and we can start from that, but then of course also other questions and topics are welcome. And we thought that the first question we put in the discussion is one of the most important ones. Just a second. Beatriz will say that at the beginning of the talk that she's a radio astronomer, she's still verified in radio data and radio service. The first question is more general for the audience. So if you think that the radio data, the radio surveys available now are useful for your science or your science question, or what kind of data do you need, do you want to have to answer your scientific goals? These are more general things. And yeah.
Yeah, so I think that the speakers both made a really strong case of why people should use lots of data in their research, and it's very, very likely that they will find a counterpart to their source in lots, even if it's not in first or last. But I'm curious if someone who is not a member of the consortium wants to use data from the international stations, how feasible is it for them to do that? Like there is a pipeline, but
the pipeline is work in progress, and as in it does work. You can do stuff with it. The data are available, and the pipeline is available. You can potentially just go off on your own and try to do it yourself. I wouldn't recommend that. I would recommend liaising with somebody who knows what they're doing in this sense. That is one of the bits where things are not quite as user friendly, because it's really complicated to reduce some of these data. But the data that are public, absolutely run away with them. Use them. And do whatever you want with them. Just I would always try and get in touch with the people who are working on this. If you want an individual source, maybe you don't need to be part of the collaboration too. If the data have not been released, then you need to be part of the collaboration. If the data are public, talk to the people who are doing the high resolution mapping and work with them with the pipeline to get your map and to get some advice on it.
Yes,
Oh.
just a follow up on this. There will be a data release also on VLBI data at some
Yeah.
point, or?
Yeah, there will be. There's already, I think, papers releasing the data for two of the deep fields where we have high resolution maps for all the sources. Eventually, I think the goal is to have, the deep sky survey everywhere and the high resolution survey everywhere. It's just this is going to take a while, but yeah, eventually all of these would happen.
3 is
Yeah, so the components and the associated component catalog will be released probably towards the end of the year, as we said yesterday in Francesco's tutorial, but the optical associations are going to take longer because again, it's the detailed inspection of this tiny fraction of sources, which is now, hundreds of thousands proportions, grow with, millions of sources. So that is what's really slowing. We want to do this carefully, and obviously we don't want to give you just something quick and bad. So it's a considerable effort, and it's going to take a bit longer. But yeah, you can just play with the radio data. If you want to do your own host associations for your sample, you can do that with the R3, probably towards the end of the year or early next year.
Can I have a very naive, maybe question about radio? So for the source of the radio, normally I know that this AGN, this star-forming galaxy, they give out radio emissions. But since you mentioned there are more radio sources than galaxies or than those counterpart when you do the overmatching. So I was wondering that are there any kind of other physical orientation can generate this radio source, some radio signal or something like that?
So for star-forming galaxies, with the emission we detect is free emission. And it comes from supernova explosions,
Those normal things, but
Yeah.
that's wondering that maybe there are other kind of source we don't know or something like that. Or...
There's multiple ways you can produce radio emission, but the dominant ones are jets and star formation. Synchrotron emission from jets is, it's a lot more, you produce a lot more of that, and then star formation, related emission than anything else. There are all the ways to produce radio, it's just, by orders of magnitude, these are the dominant processes. The problem is, you can detect this to quite far away with these, particularly the low frequency stuff. It's very sensitive. You cannot find the hosts because your optical surveys are not deep enough, or because the sources are obscured, for example. When we started incorporating WISE into the cross matching, we found many more sources. We found, for many sources where we didn't see a counterpart, they started turning up on WISE because they're obscured. You can pick them better at meaningful red than you can pick them in the optical. But even there, some of these things are relatively shallow. So when you go to the deep fields, when we have exquisitely deep data, you can recover them. For the wide fields where the coverage is a bit more patchy, the optical surveys are shallower, and we it's more uniform than things get.
I thought okay, anyway, we can.
Yeah, I'm wondering, if there's the advances here, I got the impression, I didn't realize how much new data is out there. It's amazing. And something that, and I see all these FR2 sources, thinking from a simulation perspective, simulations will put in quasar mode and then radio mode at base time. Currently, jets happen in the early universe at So my question is how feasible is it to detect radio jets emanating into the CGM and into the IGM in other environments at higher redshift?
Yeah, so it's tricky, and this is one of the reasons why I worry that we're not prepared for the FKA, because we have many assumptions based on our, we don't know how those are going to translate. So when we look at the evolution of the lurg and herd populations, for example, how these things change. As we go to redshift 2 and 3, everything was happening. These big FR1s that you see in galaxy cluster centers, it's a lot easier to push them into a high accretion regime because the black holes are smaller. So part of the problem of things being radiated in efficient at low redshift is, there's only so much gas you can push into a black hole. And if your black hole is really huge, to push it onto the radiatively efficient, Eddington threshold, you cannot do that. As the black holes get smaller at higher redshift, it's a lot easier to trigger the radiatively efficient regime. So then, how many of these lurgs are there? These regime that dominates at low redshift. How much of it do we recover at redshift? Since we are finding that, even in smaller black holes, we do see this lurg activity, then maybe this is more relevant than we thought. But yes, at higher redshift, this is a big unknown, even though these curves look very pretty and, there's some scattering here, but it's not huge. We still don't know for many of these sources, what we're missing. We're pretty complete, particularly in the deep fields up to redshift 1. Our SED fitting is quite reliable up to about 1.5, but things become pretty uncertain after that because things really change. So a lot of the answer is, we don't know what we're going to find. Or, which of these phases coexist? Can we have winds and jets at once? Can we go super Eddington, for longer than we thought? What are we going to do? How are these jets generated? Is that very different from what we see? And obviously the environments are also very different. We don't have massive clusters, we have groups. So it's a completely different regime there as well in terms of interaction.
And you have inverse Compton there.
And you have, yes, and you have an excellent point. You have inverse Compton to worry about. Inverse Compton losses become a lot higher.
So basically we have to wait for SKA to constrain it so that we can figure out how much radio mode to put into simulation, AGN prescriptions versus quasar mode or something like that.
I think we can figure out the physics at low redshift for some of these processes, and we already have JWST, and some of the data we get are really deep. Again, we do find sources at redshift 4 and 5 with low power. So we have a few sources that we can start studying as long as we keep in mind that this is not the bulk of the population. It's just Moncrief bias. They're just the luminous sources that we can find. So we can start doing some of the physics in preparation for when we have the data from the SKA correctly. I think this is work that we need to do.
I think we have follow-ups things on this discussion, right? So first and then something.
So kind of to carry on with this thing of comparing to models, wouldn't the first order comparison to luminosity function be good enough? Maybe multi-band? I mean, obviously the data is good enough for that.
Yeah, I think so.
Much the extent and the age. What would it take to incorporate this into models? I'm asking kind of the theoreticians in the simulators in the room. Was it done I thought it was done in the past, but it was just with semi-analytical models.
Yeah, I think the problem is, we're on a multi-scale problem. You need the finer resolution to trace some of the physics, but you also need the large scale to be able to, do these on a cosmological scale. And I think that is where things have not been possible in the past. I think we are at the point where this is becoming a bit more realistic, and with boundary conditions from one thing to the other, we can potentially do this. So some of these physics happen in fairly small scales, even though the effect is at very large scales. And that's I guess, the tricky bit to me. I'm talking
From simulation scale.
Coffee was first and then.
Yeah, so I wanted to follow up on the models and the assumptions that you're talking about. What is our kind of next step in converting to jet power from radial luminosity other than these scaling relations? Like how can we then towards getting these idealized jet simulations with actual physics in a statistical sense? SKA as well, or for other.
I think this is where we need to work hand in hand with simulations. Again, observations, we're kind of hitting them, particularly in the X-rays, unless you suddenly, you launch a super Athena tomorrow, we're not going to get better X-ray constraints on these things. We're limited by what we can observe. And I think this is where simulation can really help. If we give you different physics, can you simulate these things for us? And then we can see whether they reproduce these observations. And can we make, do they give us realistic physics of what we observe for this environment, for example? I think this is where we need to have an iterative process working with simulations and observations.
Yeah, there are cases where you can try to estimate the integrated jet power also only using the radio data, but you need to add a lot of assumptions there. And we did it with M87, for example, because it's a very well-known source, because we have very good resolution, we have wide frequencies, so we could estimate the aging relatively well, but you have to assume a lot of things, for example, on the magnetic fields, that is part of the aging model that you have to use. And those things are very uncertain. You also need to assume the particle content of the jets, because that also makes a very big difference in the final estimation of the jet power using only radio. So at the end we came out with an order of magnitude thing that has a lot of assumptions behind, but I don't think that this is easy to do on a very large number of floors.
So my question was, I think it was one that Beatriz asked about SKA and are we prepared for SKA? And yeah, so I guess this is going to be reaching the microjansky, maybe even nanojansky regime, where we're going to be seeing radio luminosities, which are predominantly star formation and maybe individual supernovae, right? So at this level, should we even care anymore about the AGN? Like, I mean, it's an open question, right? Like, I'm not giving an opinion on it, but I mean, like, at this level, they're effectively radio silent if you can't disentangle the two. Should we care about the AGN at that point in terms of the radio jets or not?
I think as long as I mean, my concern really is on how careful we are, extrapolating from assumptions at low redshift onto these populations. I think jets can still definitely play a role. How much of a role the SKA will tell us, and where exactly the energy is being dumped and how it's being dumped, the SKA will hopefully tell us. It's the same with everything. Again, like this question on winds and jets, which one dominates? Does it really matter whether you have a wind or a jet as long as you produce a shock and you're doing the same feedback? If the physics are right, does it matter what you call it? I think it's similar. As long as you can get the right physics. It matters.
As a follow-up, if it does matter, then how do we disentangle?
Yeah. So again, the brightness temperature thing, for example, that we can do at low redshifts with where you can physically separate the emission from star formation and the AGN. If we have enough populations where we can do this, if we have a large enough number of sources, this is now being done for tens and hundreds of sources, we can extrapolate this to thousands. We can get very good relations to help us separate these things where we don't have the resolution. And again, we will have very high resolution LOFAR observations for many of these sources going into the SKA era. So LOFAR is not going to disappear, it's still going to be doing things in the sphere. So I think combining methods, and again, we have LSSD, we will have JWSD, hopefully for a while. I think we just need to be careful about how we extrapolate this, but I think we can do this, at least for some sort of.
If I can add just a follow-up on this. It's true that brightness temperature is probably the most reliable method that you can have with radio data to identify sources that are you are quite sure to be AGN. Currently, with the current radio data, it's possible to do only with very few data at low frequencies. And
you're going to get into the brightness temperatures, which could be supernovae.
I think that usually the threshold for 10 to the 4 in terms of brightness temperature, 10 to the 5, 10 to the 4, and the brightness temperature give you quite a reliable, almost very reliable threshold for AGN activity. And then, as Beatriz was saying, once you have a very large sample, you can also calibrate other possible radio selection techniques. Like, for example, you can, provided the AGN selection with brightness temperature, you can calibrate radio excess selection technique based on other parameters that can expand even more your selection, I think.
I mean, I just want to make a probably trivial point here that essentially what you are describing is radio surveys moving to the regime of, let's say where infrared surveys are right now, right? Where you're reaching the confusion with your galaxies. And there, I mean, infrared survey haven't stopped trying to find for AGN, just they need spatial resolution, spectral information, spectral resolution. I mean, you have more tools that you try. I mean, there has been circulating around in various papers very simplistic scaling relation between AGN and star formation, assuming main sequence of star formation and black hole galaxy scaling relation. And so this confusion level between star formation and AGN, roughly speaking, happens already when you are a few percent of Eddington for optical surveys and infrared surveys. For radio surveys, you gain 1.5 order of magnitude. It's easier to find AGN, but at some point you reach this confusion. The X-rays still win. So in X-rays, because X-ray emission from star formation process is so weak, you still need to be, it's only a 10 when your accretion rate is, a 10 to the minus 4 or 5 Eddington, where you start being hit by confusion. So eventually, Athena, surveys with X-ray telescope will come to the rescue and facilitate finding weaker AGN. But until you get there, you have to use all the tools that you have, spectral information, spatial solution, and so on.
Be honest, I mean, I think you can still do it with radio, as in, you don't have the problem of obscuration, and you don't have many of the complications. For at least radio regime, you don't have to worry about emission lines. Everything is a power law, and star formation and synchrotron from AGN follow different power laws. So they follow different power laws with different spectral indices. It's just you have to
spectral information.
You have to constrain those very well because they're quite similar. You're in a very narrow parameter regime, but we will have the statistics to do it. I think if anything, it is easier to break this confusion limit in radio than it is in.
Can you clarify the spectral index thing? Because I think there's a large variation.
There isn't.
AGN.
Yeah, there isn't, and it depends on again on this spectral aging thing. So if you start, if you move from active to non-active, some cases are clear, some cases are not. Where you have mixing of different electron populations, that's what things get smeared. Or if you have, renewed particle acceleration in some loci, for example, in the hotspots of FR2s, you can get spectral indices which are a lot flatter than this because you have reacceleration at these higher frequencies.
Fusion is going to come in because these things are very compact on small scales.
Yeah, and the self-absorption, there's other things you need to worry about. But I think we can still, other than in specific places where you have the physics that are reaccelerating things, I think we can, on an integrated galaxy scale, you can probably separate star formation and AGN if you do it carefully and if you have large enough samples. There will be places where this is not possible, and there will be complicated physics, and I'm sure same as LOFAR throwing this curveball for us, where we have Tom Bombadil here looking at us. We have these very complicated structures that we find in these filaments in clusters with exciting physics, but at the same time, how the hell do you make this, and we need to figure things out. I think the SKA is going to do similarly, as in it's going to throw a lot of curveballs at us that we need to figure out in terms of the physics. But I think we can do at least some of this if we're careful and if we start preparing for it.
Yeah, there are like works that we are doing now, trying to use the spectral index to derive spectral index for injections, and yeah, there is variability there. Then you have to add other information. So by spectral index alone doesn't tell the whole story. So now, for example, we are adding the size of the sources and whatever we know about the morphology, and this is helping in trying to understand what you are looking at when you see the integrated spectrum. We are doing it on large, like nearby sources, because there we can disentangle part and see. And we are hitting, there is the difficulties of using just the integrated spectrum. So that is what you need to do at high redshifting.
Yeah, I mean, at high redshift, your resolution won't resolve everything. I mean, even with SKA, you'll have half an arcsecond, right? So, and then the galaxies are kiloparsec. I mean, maybe your jets are kiloparsec. You're not going to be able to disentangle them with parts.
So there are some cases in some results.
There are some cases for sure, but I mean,
but not
getting into the.
Yeah, that's what I say. From non-statistical samples, even at low redshift, if we know the physics, then it's fine. It's knowing the physics, even if you can't resolve them. If you know the various contributions, and you can get these information. It's getting to that point.
Yeah, on a slightly different topic and maybe slightly naive, but on this question of radio loud, radio quiet dichotomy, I mean, the sort of old school view is probably that only a fraction of AGN launch a jet, maybe those with the highest spins through the Blanford's-Naik mechanism or something like that. Is what we're saying now that actually everything launches a jet, and it just depends on the power and or where the jet deposits its energy. Is that what you were arguing there, that jets are universal?
They could be. We don't know yet. So we know in X-ray binaries this doesn't happen. but AGN are not X-ray binaries, and we still don't know what launches a jet, but there are different mechanisms proposed, and one of them, which I think has been quite successful, is the magnetic flux accretion rate onto the black hole is a lot higher in AGN because you have much bigger things than it is in X-ray binaries, and that's why you can launch a jet high soft state. So what my point is, if you're only focusing on things that you can detect in the optical and X-rays, you're missing 90% or 80 or 90 or 70% of the population. So 10% of your X-ray AGN might have large scale or powerful radio emission, but you're also blind to all the things that have powerful radio emission and don't have bright X-rays. On the other hand, even that fraction is not good enough, because if you go to deeper radio data, all of those things that you thought are radio quiet, they still have jets, they have tiny ones. I think it is possible that everything will have a jet. It's just, how important that jet is the key.
But this is critical. I mean, because if you want to, for example, invoke the jet as being the radio mode feedback mechanism, you need it to happen in every object or every massive object, right? At least at some time.
Not necessarily. Again, it's what dominates, right? So it's not a dichotomy. It's what is the dominant mechanism. So for things that most of the energy is going into X-rays, then radiatively driven winds and radiation are the dominant mechanisms, and those are the ones you need to worry about for simulations. Where you have jets that are actively doing something, so from fairly low powers, we can simulate those, especially for the ones that you have in galaxy clusters. The jet mode, the traditional jet mode, that is your dominating mechanism. It doesn't mean that we don't have some crossover. But for the simulations, you can do these separately and put them together in the middle.
Well, yeah, but you have to, all quenched galaxies, you have to keep them quenched. So they all have to have a mechanism to keep them quenched.
Yeah,
and if that mechanism is the jet, then everything has to have a jet or have had one.
It's not it's not an either or. You can have both. It's just what mechanism dominates.
What do you mean by both? What do you mean by both?
I think it's what mechanism dominates on which physical scales and what time scales that you have to worry about. So it's not that by having a wimpy jet you have to worry about those low power ones doing things on cluster scales. Those are going to do things within the host. And again, with winds, you have the physical parameters to constrain this. What you need to do is incorporate more physics and some of the intermediate cases into the simulation.
Well, all I'm really saying is in order to have the effect of keeping the galaxy quenched, you have to always have the cause, right?
Well, you have to have something that does it, whether it's winds or jets, and what proportion of it is winds and jets is what we need to find out.
So you're saying that there might be several mechanisms.
Yeah, and they can coexist. That's the thing.
I think here there is another one. No, I know. Okay.
I wanted to possibly counter the argument that all AGN have jets. There was a recent work that did some stacking of X-ray detected AGN in the radio, and that was reaching down to some microjansky, like the nanojansky regime, and that found actually that there are some AGN which is actually radio silent.
Yeah, good enough.
But it doesn't mean they have radio at some point. Yeah, at that point they had X-rays and AGN, but
yeah, I mean, and again, that's perfectly good. My point is, we still don't know, in what conditions you do launch a jet, even a low power one. We can't extrapolate to X-ray binaries, which are the things we can monitor for a long time.
No, but I think this what you said is something that maybe we can do much better in the next, I would say, up to 10 years, and reach depth that are much bigger. I mean, stacking in radio is a pain, and it has a lot of caveats that one has to be very, very careful. And there were a lot of.
Somebody did this. I know they know what they were doing.
They know what you're doing. No. Yeah, I think that is but I think we can do much better, both with SKA, but even with LOFADO, we have plans to go on deep fields with more than 2,000 hours on just one field, and at that point, in practice, we should be able to detect every radio emission from every galaxy that we can detect in the optical, and at that time we can try to do that.
It's a very interesting discussion. We didn't cover all our questions, but we reached the time of the discussion, and so I think we discussed it today. And Beatriz will put the slides on Slack. So the questions are still there, and
Please let us know how we can help you and what we can do for you.